Do you see me?
Yes, yes, we do.
Okay. Good morning, everyone, and welcome to this first keynote lecture of the school that will be given by Roberto from Princeton. Roberto hardly needs an introduction to any molecular simulation practitioner, and I will just say very few words about his many recognitions and the awards that he has got all along his long and very productive career. Roberto, of course, you all know the groundbreaking work that he did in Trieste in the winter 84 to 85 with Michele Parinello. And that work got immediately a huge attention from all over the world, and started to get them many prestigious prizes. The first of which, if I remember well, was the HP Prize of the European Physical Society, awarded in 1990. The two of them have got a number of other prestigious prizes, including the Dirac Medal of the ICTP and many others. And Roberto was elected as member of the American Physical Society in 2016. The last chain of this, the last link of this long chain of awards and prizes has been this year the Franklin Medal that is awarded yearly by the Franklin Institute in Philadelphia to scientists and entrepreneurs in the United States. The Franklin Medal is probably the most prestigious prize awarded, scientific prize awarded in the USA. And the previous awardees include the likes of Albert Einstein, Maria Skłodowska-Curie, and Stephen Hawking, and many others. The latest interest of Roberto include the physics of water and other H-bonded systems, with attention also to the role of quantum effects. So these are very time-consuming molecular simulations, much more so in the case of quantum simulations, including quantum effects on nuclei with path integral molecular dynamics. And this, I think, is one of the reasons that brought Roberto in contact with modern machine learning techniques that allow to combine the accuracy of ab initio molecular dynamics that he has pioneered 35 years ago with the economy that can be achieved with classical force fields. Let me conclude with this presentation with a few personal recollections about Roberto and the strong links that have always tied him to the Quantum ESPRESSO project. The great work of Carlo Parinello, as I said, and all of you remember, was done in the winter of 84-85, when Roberto was fresh from the United States. He arrived in Trieste in the fall of '84, coming from IBM laboratories in Yorktown Heights. And amongst the many things, the many knowledges that he brought back to Europe was a plane wave code that was pioneering in many ways at those times, that he brought back from IBM, if I remember well. And the main features of that code were FFTs to do convolutions, to do real space convolutions, which are one of the key technical features of modern plane wave based codes, and a very smart use of symmetries. These two features still exist more or less untouched in the modern distribution of quantum espresso. Shortly after, Paolo Giannozzi and myself started to work on more traditional self-consistent approaches to DFT, and combined ideas from Karen Parinello with those more conventional approaches by implementing, I think it was the first at those times, attempt to avoid matrix diagonalization and to replace them with modern iterative techniques. And then density functional perturbation theory came, and soon after, the many students that passed from Trieste were continuing their scientific journey, taking back home or to other destinations their own versions of the code, of the codes that they brought back, that very soon diverged. So all of the codes that are now in the quantum espresso distribution originated from the first plane wave code that Roberto took to Europe from Yorktown Heights. And soon those individual codes stopped to talk to each other and were incompatible with each other. So when I visited him in Princeton in 2002, it was the time where many other characters that all of you know were or had been shortly before in Princeton. Those characters include the like of Paolo Giannozzi, Nicola Marzari, and Ralph Gebauer. In that summer of 2002, Roberto and the other guys, including myself, decided to try a kind of grand unification of the main codes that originated from the first plane wave code brought back to Europe by Roberto in 1984. And that was the birth of the Quantum Espresso project. The Quantum Espresso project didn't have its name. We tried a few names that for one reason or the other didn't survive, but the final name was found in 2004 as Ralph told us this morning, while we were at the summer school on electronic structure theory in Beijing, and we were waiting at the Beijing airport to board for a flight to Xi'an. So I think the originator of the present name is Nicola Marzari, to whom goes the credit and our gratitude for finding out the name. So I've been talking for too long already. Let me conclude this introduction by thanking Roberto for accepting to be our first distinguished speaker. And I wish all of you a happy listening of Roberto's lecture on machine learning and ab initio molecular dynamics. Please, Roberto.
Thank you, Stefano. Let me see if I can share the screen. Share. Yes, can you see the screen?
Yes, we can.
Okay, very good. Okay, let's see that. Okay, so I would like to thank Stefano for the very nice introduction and all this recollection. In fact, the recollection on the name of Quantum Espresso is very nice, and I just remember that all the names we came up before were just awful. And finally, Nicola was able to find a very good name, and I think that makes this project really distinct from other projects of that kind. Now, in my lecture today, I'm going to discuss mostly machine learning based ab initio molecular dynamics, which is the issue, the topic on which I have been working in the last 5 years. Now, you all know what ab initio molecular dynamics does. Essentially, it solves Newton equation with forces that are derived from the quantum mechanical state of the electron. And you see in the animation here, the growth of a crystalline nucleus in water. That is a simulation done with metadynamics using a standard force field model for water. Well, that is something that could be done until very recently only with empirical force field. And the reason for that is that even though one just does classical molecular dynamics in order to find out the trajectories that give rise to the nucleation of a crystalline nucleus, ab initio molecular dynamics is very expensive, even with the most powerful computer, so that this kind of simulation was definitely out of reach with ab initio MD. On the other hand, recently there has been a very important progress based on marrying ab initio molecular dynamics with machine learning. In fact, by learning the potential energy surface from quantum mechanics, machine learning method makes possible simulation of ab initio molecular dynamics quality at force field cost. Essentially, what machine learning does is to learn the local pattern of atomic configuration that give rise to the potential energy surface, and it interpolates the result obtained from the learned pattern to patterns that are that were not included in the training data set, but which are close enough to the learned pattern, which is what happens, in fact, in molecular dynamic simulation. Well, there are several methods to do that, and I will discuss the method that was developed in Princeton. This method is called deep potential method, and it uses deep neural network to model the potential energy surface and other ground state properties that are accessible to ab initio molecular dynamics. It has been developed in the PhD thesis of Linfeng Zhang, who is now back in China, and Linfeng received a doctoral degree in May of last year, and several other people contributed to the effort. I want just to mention that besides Linfeng, Professor Wenan in the math department at Princeton, and myself were the director of Linfeng thesis. Okay, let me move on and give some detail. Essentially, we have a physical property that in the examples that I will show, at least in some of the examples, is the potential energy or the polarization or the polarizability surfaces. So this is a quantity that an observable property O that can be a scalar property in the case of the energy, a vector property in the case of the polarization, and a tensor property in the case of the polarizability. And what the deep potential method does, it represents this property as a sum of local properties, the index I run over the atoms in the system, and each local property depend on the coordinate of the atoms that belong to the neighborhood of that particular atom. These are the local pattern I was talking about before, and this is a local representation. However, the local properties depend on the atom, on the pattern on the atom that are included into several coordination shell of the I atom, and within that neighborhood, the function f is a truly many-body function of the atomic coordinate. The property f is represented by a symmetry-preserving, continuous and differentiable function of the atomic coordinates in the environment which contain variable numbers of atoms. There are some distinctive features in this approach. One is the flexibility of the deep neural network representation that allows us to model essentially any function, provided the function can be represented in terms of local properties. Well, so this is a very important feature, representing the function in terms of this local property as a superposition of local properties makes the property by construction extensive, which is important to extend the simulation to a system of much larger size than the size that are used to learn the local environmental dependence in terms of density functional theory calculation. Another very distinctive property of our approach is that the learning process can be made on the fly using an efficient approach called DPGen. I will describe later on in a little more detail. And finally, the approach has been implemented on high-performance computing platform, particularly platform based on GPUs, and has very high computational efficiency on this platform. Let me move on. So basically, as I said, the quantity that the observable property that we are representing is the energy that the potential energy surface is what is given here in the first line. Then another property that we represent is the cell dipole that I call M here. And here in the case of the cell dipoles, I specialize the description to water. So we have a dipole associated to the oxygen. The charge is 6 because we use a pseudo-potential representation, and so these are the valence electron. 6, or this is the charge associated with the ion core of the atom. We have 1 for the hydrogen, and then we have the electronic center of charge that are the Wannier function. Actually, in water system, irrespective of whether water is still in molecular structure or it is dissociated, partially dissociated into ions, these Wannier centers are always associated to the oxygen. And so we can construct an average of the 4 Wannier centers, each one with 2 electrons associated to the oxygen. We call that Wannier centroid. So this quantity gives the dipole, the cell dipole, and then the derivative of this quantity with respect to an external applied electric field at fixed position of the nuclei defines the polarization tensor, this alpha, that also has the local representation given here. So all this is described in the paper quoted below. And so this allows us to do a number of things that can be done with standard ab initio molecular dynamics, but with a much higher computational efficiency. So let me move on and just spend a few words on the deep potential generator. Now, in a neural network representation, in this diagram here, I describe a network with 3 layers of nodes or neuron, and a certain property A that depend on S that are the descriptor for these properties. So the atomic coordinate, for instance, in our case, is given by a complex functional form that depend on this parameter W and B. And this is a convolution of a convolution of a convolution. So it is a rather complex function that depends in a way that is highly nonlinear on the parameter of the network that have to be learned by minimizing the distance between the prediction of the network and the actual DFT calculation. So in the DPGen procedure, rather than performing a large number of DFT calculation or of ab initio molecular dynamics first, and then trying to describe that with a neural network, what we do is that we exploit the nonlinear dependence of the network on the network parameter, which means that if we do a minimization to find the network parameter, we will get typically the minimization to find the network parameter is done with a procedure that is a stochastic gradient descent method. So it is a method that find a local minimum. So we will get different local minima, different network parameters, if we start from a different initialization of the network parameter. So what we do in DPGen, we use a Gaussian distribution for the initialization of the network parameter, and then we select a few neural network that are generated with different network parameter. The ensemble of neural network, we have in principle an ensemble of neural network that can be generated by simply varying the initialization. This ensemble is already well represented by few members, 3 or 4 in practice. And now what happens? If the network is well trained, even though the network parameter after the minimization are different, all these members of the ensemble of neural network will represent equally well the physical property of interest. But and so we can explore the phase space with the so far trained deep neural network, and we keep following this exploration procedure that is done with molecular dynamics, but molecular dynamics guided by the neural network, which is very efficient, computationally much less costly than quantum mechanical calculation. And we measure how close are the prediction obtained with different members of this ensemble of network. As we reach a point where the predictions start to diverge, it means that the neural network is no longer good to describe properly this property at that thermodynamic condition. So we label this configuration, and we do a quantum mechanical calculation for this particular configuration, adding this particular configuration to the library of the training data, and we improve the training of the model by this additional configuration, and we proceed in this cycle until the network is sufficiently good over the entire range of thermodynamic condition of interest. So this is the procedure that we use. Let me move on now. I have described what deep potential molecular dynamics does. I will now show a few examples that are definitely beyond the reach of direct ab initio molecular dynamics simulation. The example that I will talk about today is phase diagram of a scan-based DP model, the auto-ionization of water, homogeneous nucleation of ice, and something to do with vibrational spectra. But let me just say that the very most of the calculation I will show today are based on classical MD simulation, but we are also working at including nuclear quantum effect via path integral simulation, as Stefano mentioned in its introduction. The first example is a deep potential model for water based on scan DFT functional. This work is going to appear soon in physical review letters and is available in this archive preprint. So what we did in this work, we were able to model water over a vast range of thermodynamic conditions, including crystalline phases in a range of pressure going from ambient pressure to 50 gigapascal, and including all the crystalline phases that occur in this domain at pressure for temperature extending from at low pressure from 0 to 400 Kelvin, and at high pressure extending up to 2000 beyond 2000 Kelvin. So in this vast range of pressure and temperature, there are many different crystalline phases indicated here by 1H, 11, 2, 6, 8, 7, 7 seconds, and a fluid phase that can be just a standard molecular fluid at low pressure and becomes an ionized fluid at high pressure. Now, the red line indicate the boundary line between the different phases that were obtained with the DP model. The gray line indicate the boundary line that are actually the correct boundary line as obtained from experiment. So we can see that overall, the qualitative picture is quite good, but there are deviation from the prediction of the model, which is essentially the prediction of this particular DFT functional for this system, and experiment. I want to show here, there is in this small phase diagram here, is the prediction obtained with one of the best available empirical potential model for water compared with experiment. We see that there are deviations from experiment also with this model, and particularly this model become particularly bad as we go to high pressure, because at high pressure the ice rule that characterize water structure at low pressure are broken more often, much more often than at low pressure, giving rise to partially ionized configuration. But these partially ionized configuration are not possible with a rigid water model as TIP4P. Instead, they are possible with ab initio MD and with the deep potential model. I want to mention a couple of more things here. Here we have I6, but there is also ice experimentally at low temperature, ice 15 would be the most stable structure, but ice 15 is only metastable within the deep potential model. This might be related to the difficulty of stabilize the phase ICE 15 with standard semi-local functional. And also this ICE 3 that is stable in this small region here experimentally is only metastable in the deep potential model. That might be due to the fact that the boundary between ICE hexagonal ICE and ICE second is pushed at higher pressure with this model. And also you can observe that the melting line of ice, of hexagonal ice, is pushed by about approximately 40 Kelvin at higher temperature compared with the experiment. Now, this simulation were all done with classical simulation. And so there will be correction due to nuclear quantum effect, but the correction that will be, I expect those corrections to be smaller than the deviation of the model from experiment. So what is interesting about that is that a single deep potential model can describe water over this vast range of temperature and pressure. In order to learn the local pattern in this vast range of temperature and pressure, we explore this huge phase space with the deep potential, and we had to perform less than 35,000 DFT minimization to construct the potential energy surface, which is approximately 0.05% of the total configuration visited with the DPGen technique. The error in the free energy that we estimate is approximately 1 milli-electron volt per molecule. Of course, this is much better than chemical accuracy, but this is the error compared to the DFT reference. So the deep potential representation is really quite accurate. I want to mention just one more point here that has been possible, I think, for the first time with this simulation, and that consists in the study of the transition from ICE 7 to ICE 7 second and then to the ionic fluid. Let's suppose that we move on a isobar over here, and if we move along this isobar, what we see that I7 that is still a molecular system will start developing ionic diffusion as we increase the temperature. Ionic diffusion starts to grow exponentially with temperature, and eventually it saturates. Right before saturating, there is a more rapid variation in enthalpy and volume, and but this variation in enthalpy and volume in simulation here that were done with 432 molecule cell appear reversible. We can go up and down here, and there is still this more rapid variation. What we could do with this simulation that could not be done before, we could study what happens to this rapid variation here if we increase the size of the cell. We went to 3,000, approximately 3,500 molecule, and what we see a sharpening of this rapid variation region, both in the enthalpy and in the volume. So this is consistent with a weakly first order phase transition between I7 and I7 second. And indeed, a year or so ago, that was found also experimentally, that this superionic transition that occurred between I7 and I7 second is a weakly first order transition. I will not spend more time on that, but that is just to say that issues like finite size scaling that are important to assess the nature of a thermodynamic transition become possible with deep learning. Let me move on and discuss another example that well, that has still not been published because we are studying the effect of nuclear quantum on that, nuclear quantum effect on that, but here I will discuss only at the classical level. So we know that the self-ionization of water is what gives rise to the pH of water, and a quantity that is called the Kw, the K factor of water, is given by the product of the concentration of the ions that are due to the dissociation of the water molecule. I have here an animation that shows the recombination of these two ions. This animation was obtained by Chunil Zhang at Temple University, and it shows a recombination process as first described in a paper by Ali Hassanali and the Parinello's group, which was published in the proceeding of the National Academy of Sciences in 2011. So now we can describe these processes with deep potential molecular dynamics, and now, even though the recombination can be studied, can occur spontaneously if the ions are close enough, the dissociation required enhanced sampling technique, and in particular, we use here metadynamics, and we use a reaction coordinate S that has been recently introduced in the Parinello's group, and is based on the Voronoi tessellation of the system of the disorder structure of the oxygen in the system. You see, with traditional collective coordinates that are based on distances, one has this spherical distribution, and one recognizes if the ions. So the difficulty in this simulation is the fact that as the simulation proceeds, the proton keep diffusing all over the place, and so it is difficult to keep track of which ion is which. And if we use coordinates, the spherical, that depend only on the spherical distance, you see that there is an overlap between this region that is associated to the hydronium and this region that are associated to neighboring water molecule. So if we are in the overlap, we do not know if the hydronium is here or if it is there. Instead, with the Voronoi tessellation, this effect does not occur anymore. And then we can study this thing with the reaction coordinate that has this form suggested in the paper in the Parinello's group, and we can then compute the quantity that is the pKw, that is the logarithm of the quantity Kw, and we can study this thing as a function of system size. And in fact, we see that we have, this corresponds to a system with 500 molecules, and this corresponds to a system with 1,000 molecules. We see that we achieve convergence with respect to size only with sizes that are beyond what would be possible with ab initio MD. And now we do this system here at 330K ambient pressure, and using a deep potential model based on the scan functional. What we get for the pKw for heavy water, we did the comparison with heavy water rather than light water, even though for us it would be the same to use one or the other, simply because this is based on classical simulation, and heavy water should be closer to the to the result of the simulation. And we see that the agreement for the pKw with experiment is rather good. So these are difficult properties to predict from first principle, but now it becomes possible to do it. Let me move on and describe another example. In this other example, we consider nucleation of ice from seeding simulation. So I will describe, essentially in a seeding simulation is a simulation in which nucleation is studied by inserting a seed, a crystalline seed, inside a liquid, as I will describe in the next couple of slides. And then one uses the result of this seeding simulation together with classical nucleation theory, CNT, in order to obtain the nucleation rates. But before doing that, we need to study the difference in chemical potential between solid and liquid at various temperature from enhanced sampling simulation for a scan-based deep potential model. And the result, the chemical potential difference as a function of the supercooling of water is represented here. So in the difference in chemical potential, the supercooling is the supercooling that one has in the model. So in experiment, the supercooling is supercooling with respect to the melting temperature of ice, that is 273 Kelvin. In the DP model, the melting temperature is around 310 Kelvin, as shown here by this coexistence calculation. And so it is supercooling with respect to that melting temperature in the model, and similarly the supercooling for the tip 4P ice is supercooling with respect to the melting temperature of tip 4P ice. And we can see that as a function of the supercooling, the difference in chemical potential that can be obtained with enhanced sampling simulation is indeed techniques again developed in Parinello's group, and I've been happy of having the opportunity to collaborate with Pablo Piaggi, who received the PhD under the direction of Michele and is now a postdoc at our center at Princeton University. So you can see that actually the deep potential model, if it is compared to experiment in this way, looks describe the difference in chemical potential better or slightly better than the T4P ice, in spite of the fact that T4P ice has a much better agreement with experiment for the melting temperature. Now, again, this is what we do. Now let's go to the seeding simulation. And first, let me remember, well, I think here I haven't had the time to do to check on the animation of the way the different things are indicated here. So the rate are derived from this expression, that is the expression given by classical nucleation theory. So essentially, the difference in free energy between the solid, that is this solid nucleus that has been inserted here, in the liquid around, depend on the fact that one gain in free energy in the bulk solid, but one lose in free energy at the interface. So one has this expression for the difference in free energy. Where is that? The r to the cube, I cannot see, well, doesn't matter. The r to the cube gives the dependence on the volume of the nucleus that is supposed to be spherical, and r squared gives the dependence on the surface. It is a cost of free energy because of the mismatch between the solid and the liquid at the interface, but for sufficiently large volume, the bulk stable phase will gain. And indeed, if we perform a simulation as shown here in this upper diagram on the right, we monitor the number of ice-like configuration at different temperatures. You see that when the temperature is low, the ice-like structure decrease with time. Time is of order of nanosecond here, and the structure grows at the higher temperature, but and remains stable in a small range of temperature. Now, the expression for the rates is given here by this expression here. So we see that the difference in free energy, the C, indicate the size of the critical nucleus that can be found in the simulation that I just described. This gives the thermodynamic factor, but there is also a dynamical factor that depend on Z and F plus in addition to the density of the fluid. Z is what is called the Zeldovich factor, and F plus is the kinetic prefactor. That is something that one can also observe in the simulation, which is the accretion rate of molecule by the crystalline nucleus. The Zeldovich factor has an expression, an analytic expression in terms of delta mu, the temperature and the critical number of crystalline molecules within classical nucleation theory, and essentially gives the probability that when one is on top of the barrier here, separating the region where the nucleus is unstable and the region where the nucleus is stable, this gives the probability that if one sits exactly on top, one would go on the growing side of the nucleus rather than dissolve by going back. So similar to what one does in rate theory for defects, for instance, in solids. And now here are just two simulations. This simulation here include 12,000 liquid water molecule in total and 600 molecule in the cluster. And one can see that at this temperature, the cluster reduces its size, whereas at this temperature, the cluster increases its size. Well, if one put together this result, now this is now the point is that the lower the supersaturation, so the lower the temperature of the supercooling is, so if one is at higher temperature, the simulation need to be done with larger sizes of the system and larger sizes of the cluster, because the critical nucleus will be larger at this higher temperature. And so in fact, we have simulation running out now with more than 100,000 water molecules, all at the ab initio MD level. And let's see how the results are for the simulation rate. Here, these are experimental data point. These are the results with T4PIs, and these are the two simulations that we have done so far, and then we interpolate with classical nucleation theory, we get this green line. This is the result obtained with the MW and other empirical potential model for water. And now what is this green region here? The green region here is the uncertainty in our simulation, simply due to the uncertainty for the critical temperature estimation. If we have, we estimate our uncertainty in the estimation of the critical temperature to be plus or minus 2 Kelvin. With plus or minus 2 Kelvin, you see that one has all the nucleation rate could occur within this green region. So the important result is that the ab initio result for nucleation rate and surface free energy are in the right ballpark, and the result from ab initio theory are actually not in bad agreement with experiment, given the uncertainty and in this very delicate quantity. Now, let me move on. I mentioned vibrational spectroscopies, infrared and Raman. Here, using the cell dipole or using the polarization, one can compute correlation function, time correlation function, and from this time correlation function, one can obtain this quantity that is actually related to the imaginary part of the dielectric function that gives the absorption, and you see the comparison between theory and experiment. Here again, temperature dependence of the Raman scattering cross-section at very low frequencies, in which in this region the intensity in the Raman spectrum is approximately 2 orders of magnitude lower than the frequency in correspondence with the stretching modes that are the most give rise the higher intensity in the spectrum, and so it is very difficult to get result over there. But not only could we get the result, we could also study the temperature dependence and compare with experiment with this simulation based on the deep potential model. let me just spend a few words here on the effect of the DFT approximation. And here I don't do any shift. I report experimental data for the density of water, liquid water, and ice. Well, the data point for ice should go at up to the melting temperature, that is 273. But anyhow, that's the how it behaves. And so you see that there is a discontinuity in the density going from the solid to the liquid in experiment. That is the result with scan. The discontinuity has the right size, but it's smaller than experiment, and everything is shifted to higher temperature. We also see that in the liquid, there is a temperature of maximum density that is approximately here. In the scan, there is also a temperature of maximum density that is approximately over here. Now, if we go to hybrid functional approximation, this is PB0 TS, we see that it improves a little bit with respect to scan. And here we have the hybrid version of scan, in which we include 10% of exact exchange, exact Hartree-Fock exchange, and we see that the discontinuity is approximately right, and also the results are pushed down to lower temperature. We have some preliminary data using path integral molecular dynamics, and with this preliminary data with path integral molecular dynamics, we see that the temperature of maximum density is pushed down to approximately 290 K, not too far, well, approximately 10 K above the experimental results. So we are quite confident that by climbing the Jacob ladder of density functional theory, one can improve also on these delicate properties. And since we are talking about quantum espresso here, I want just to report a couple of slides that I received from Xinyu Ko and Rob DiStasio. Rob is a former postdoc in Princeton, who is now a professor at Cornell University, and Xinyu was a former student in Princeton, who is now a postdoc working with Rob, and Biswajit Santra was also a former student at Princeton. So they have developed within the quantum espresso a technique to compute, a linear scaling technique to compute the exact exchange. And this linear scaling technique is based on using a representation of the wave function based on maximally localized Wannier function. The code is available. This is the alpha EXX version that is currently available in the CP module in quantum espresso. It allows to do both NVE, NVT, and NPH, NPT simulation with variable cell, and include the contribution of the variable cell to the exact exchange. And the code scale quite well with massively parallel computer. There is a version that they are developing right now, and which will be accessible in the near future. And in this version, it has modified the way of taking advantage of the localization of the Wannier function in a way that is much more efficient, so that it can achieve a speed up of 6 compared to the alpha version for liquid water, a speed up of 15 for a system TiO2 and water interface. So the more heterogeneous the system is, the more the approach, the beta approach is effective compared to the alpha one. And the 30 factor of speed up for metal doped molten salt, for metal doped molten salt. So that is a capability that will be added to the quantum espresso soon in the future. So at this point, I think I've used all my time. I want to just spend a few words on conclusion and outlook. So deep potential molecular dynamics is several orders of magnitude more efficient than direct ab initio molecular dynamics, and has linear scaling with size due to its local representation, opening the way to studies well beyond the reach of ab initio molecular dynamics. Complex phase behavior, reactions in solution, nucleation, dynamic response. Deep potential is a proxy for density functional theory. Quantify the model deviation from the reference is important, as I've shown in the deep potential method, DPGen description. Algorithms to achieve this goal are crucial. For example, the spread of a network ensemble, reweighting of deep potential data I've not talked about, but they can be reweighted since the deep potential is so close to the ab initio molecular dynamics to get the true prediction of ab initio molecular dynamics for configuration based on the deep potential model, etc. More properties are accessible to first principle calculation. And therefore, this provides a wider check of DFT approximation. There are a number of issues. The local representation does not describe explicitly long-range electrostatics, which may be important in a highly heterogeneous system. And the whole issue of quantum correction is open. Quantum correction to statics, that can be done in principle exactly with path integral simulation, but there are also quantum correction to dynamics and spectroscopy, which require approximation because of the sign problem in sampling the appropriate correlation function. And then there is the issue of chemical accuracy, DFT, and beyond. With that, I thank you all for your attention. And of course, there are many people whom I should acknowledge. Some of them were mentioned here. I want to recall again Lin Feng for his fantastic work in developing the deep potential method, and also Han Wang, another collaborator from China, who has been behind many of these applications, in addition to the people currently at the CSI Center in Princeton, and of course, the Department of Energy for supporting us. Thank you.
Thank you very much, Roberto, for the fantastic lecture. I don't know exactly how to proceed with the discussion. Probably the best thing would be that participants wishing to ask questions do so in the chat, in the Zoom chat, and I will read the questions to Professor Carr.
Yeah.
So let me just break the ice. Would you tell us something, Roberto, about the prospects for the open issues that you have mentioned? If there are any progresses that you see around the corner concerning quantum corrections to dynamics or long-range interactions, any of those problems, can you mention a few,
yes, I can
lines
mention.
of research?
In fact, long-range electrostatics is essentially there. We have a code. Again, I'm collaborating with Lim Fong, Han, and Weinan on that. We have already a code that is not yet public to deal with that, but it works, and essentially it is based on using the ion charges and the electronic charges given by the Vanier function, Vanier center, to describe the long-range electrostatic. The long-range electrostatic with this charge center is enough because at short range, everything is taken into account by the deep potential. So one can separate the long range that is taken into account with Ewald kind of technique and deal all the rest with the deep potential. This kind of thing works and shows that in typical bulk situation, somehow the deep potential is able to take care of the effect already with the short range part. Of course, this is even in the bulk, this is not completely true, because if you are looking at longitudinal optical splitting of the phonon in ionic material, that will require long-range electrostatic. But for most of the properties that I mentioned in the example that I considered before, this long-range electrostatic is not important. But as I said, there are cases in which it is important, and we find that it can be taken care of again using the Vanier function. In principle, we could also use information on the spread of the Vanier function, but so far we haven't found that to be necessary. Just the center is enough. Then there is the issue of quantum correction. Quantum correction is tough. Is a tough problem, quantum correction to dynamics. Quantum correction to statics, we can do, and we are studying how they affect properties, and by doing path integral simulation, and there again, different functional, the combination of functional and quantum correction is important to understand this effect. Now, in the case of quantum correction to dynamics, unfortunately, one has the so-called dynamical sign problem due to the fact that the dynamic correlation function that one is interested in is a complex quantity that is widely oscillating. So there is no way of doing the calculation exactly, at least so far. There are various methods, like for instance, ring polymer molecular dynamics, centroid molecular dynamics, or linearized approximation for the Wigner dynamics, and these are all semi-classical approximation which, however, for a system like water may work. We are studying them, and we are also combining them with maximum entropy method in order to include effect beyond the approximation that is unfortunately uncontrolled, to give some control, let's say, over the uncontrolled approximation of the various methods that I described. So we are studying this thing, and I think that for systems like water, it is possible that in the future it will be possible to include this effect.
Okay, now there are a number, thank you very much, Roberto. There are a number of questions that are flowing through the chat. I will take the liberty of selecting among them. There are two general questions, one directly related to your talk, the other to the general field of ab initio molecular dynamics. You may want to take them together or just one of the two. Two participants are asking you some clarifications about the relative merits of Carparinello and the Born-Oppenheimer molecular dynamics. The other question are related, but on the same style, relative merits of deep neural network machine learning techniques and Gaussian process, kernel methods based on Gaussian processes.
Yeah, these are good questions. So let me start with the one on Carparinello versus Born-Oppenheimer. Well, I don't see the Carparinello versus Born-Oppenheimer as two separate ways of doing ab initio molecular dynamics because the Born-Oppenheimer condition can be satisfied sufficiently accurately with Carparinello molecular dynamics, and in fact, in the limit in which the fictitious mass goes to zero, it will be satisfied exactly, and also because the iterative way of doing Carparinello molecular dynamics is essential also to do Born-Oppenheimer molecular dynamics. In fact, we have nowadays schemes that are also available, I think, within the quantum espresso, both in the CP and in the PW module of the quantum espresso, by which one can enforce the Born-Oppenheimer condition in an iterative approach. Now, at the beginning, when we developed the Carparinello method, we also tested the exact, let's say, condition to impose exactly the Born-Oppenheimer condition, but it was much more expensive within our iterative approach, but it was much more expensive than doing the Carparinello with a reasonable value of the fictitious mass. So at that time, we didn't even write anything about that, but we should have done it. One more thing here. nowadays, with much more powerful computers that are available, it is important to satisfy, particularly as we go to this accurate calculation, it is important to satisfy the Born-Oppenheimer condition as closely as possible. This is particularly important to construct deep potential. So this is now regarding the second question. Of course, there are various different methods to use machine learning, and there are various groups who have developed methodologies to do that. As I said at the beginning, I was just going to discuss the methodology I was involved in. Again, one can distinguish two general groups. One group that is based on deep neural network, and one group of methodologies that are based on these Gaussian processes on kernel method. As I can see, the advantage, or one advantage that I can see with deep neural network is that deep neural network can represent really very complex functional behavior. In fact, can represent essentially any function. And the difficulty is mostly then in the learning process, because the learning process can be a process that is NP complete. So the learning process is difficult, is hard, while the deep neural network representation can represent essentially any function. Now, I don't know how well that can be done with kernel method, although from the result that I've seen, kernel methods seem to be work quite fine. So that is the only thing I could say. I must add just one comment. I asked my friend Wenan, who is a professor in mathematics and understand better than me the complex subtleties of those things. And one thing that he told me is that while I understand why deep neural network work, I still don't understand why kernel method do. That is his, that was his question on that. Maybe we should keep discussing that more to try to understand that better.
There are a couple of related questions on molecular absorption on molecules, on molecular absorption on surfaces, and another related question was about the ability of neural networks, neural network potentials present or future ability to mimic weak molecular forces such as van der Waals or intermediately weak forces.
Yes. So the first one was, okay, what was the issue on absorption?
Molecular absorption is related, I would say. So one participant was asking about the ability of neural network potentials to predict the molecular absorption. The other one was more methodological, but the two are related, I think.
Okay. Well, of course, absorption can be chemisorption or physisorption.
Let's say physisorption. Let's say physisorption.
Okay. So
or intermediate.
Okay. So of course, the neural network doesn't discover yet new quantum mechanics, and so it gets out in output what it gets in input. So far, the examples I presented used network that were trained mostly with the scan functional. The scan functional is a meta GGA that was developed in the last decade by John Perdue and collaborators, and has the ability to describe also what they call intermediate van der Waals interaction. In fact, we get a decent description of water without having to add additional van der Waals interaction. I like that because it is within a seamless approach. However, while these things seems to be working sufficiently well in a system like water, it does not work well for system in which the van der Waals effect are even more crucial, and the interaction that keep the system together are weaker, like for instance physisorption or organic crystals, so crystal made by organic molecules. In that case, we tried in some organic crystal or some case in the past, the scan, although slightly better than PBE, would not work. And in fact, adding van der Waals interaction is important. Now, van der Waals interaction, there it is important to do something. I mean, the way in which van der Waals interaction are added in most calculation is just by doing a sum of two-body term, which, however, is already a drastic approximation to the van der Waals interaction, because a system is really described by two-body terms only if it is two-body. So to go beyond that is difficult, and for instance, Alex Tachenko and also Rob DiStagio and other people have made progress in that direction. I think that this technique could be also included to some extent in the potential, because the local region of the deep potential or machine learned potential, in the example I've shown today, we use a radius for the local environment of 6 angstrom, but one could go beyond that, let's say 8 angstrom or so, still would not be exceedingly expensive. So that is something that can be done. So the effect in this range of the van der Waals interaction could be learned, and effect beyond that, that would be much weaker, could be included, like we include the long-range electrostatic interaction in the case of the equal summation. So there are possibilities, and we are not involved in that concerning van der Waals, but I'm quite sure that there are people around in the world who are working at that right now.
Okay, I think it's painful to cut such a lively discussion, but I think it is high time to close this afternoon's session. I would like to thank Roberto again and all the participants to stay with. For having stayed with us thus far. Thank you very much to all, and for the participants, we reconvene tomorrow morning European time. With Roberto, I wish we will soon meet in person. Thank you very much again. Have a nice day or night or whatever it is at your place.
Thank you.
Thank you, Roberto. Thank you very much.
Thank you.
Thank you. Goodbye.
Thank
Goodbye.
you. Bye, Roberto. Bye.
Bye. Bye. Let's see now the stop share.